Okay, so here's the video that goes with magnets and magnetic fields, and you should have the PowerPoint out and a calculator also. So I think that you guys have generally a general knowledge of magnets and how they work. You used to play with them as kids, I'm sure, a lot. We didn't really cover them last year much in the honors physics class, but we're going to cover them in detail in this class, and specifically how magnets and electricity are related to each other and how they affect each other. So that's what we're going to be working on. So we're going to start with just plain magnets and magnetic fields, and we'll kind of work up from there. So some things about magnets which you probably know already. First of all magnets have a pole, which is we call them the north and the south, and they create fields around them the same way that electric charges create fields around them. Every time you take a magnet and split it, a new north and a new south is formed. And this is something that's different than electric charges, because you can have a single positive or a single negative electric charge and they can exist on their own. But with magnets you can't have a single north or a single south pole. They have to be together. So every magnet has both a north and a south pole. And they exert forces on each other at distances, so they don't have to touch, so they have field forces. Magnets can be permanent or temporary. Permanent magnets are probably the ones you're familiar with in terms of magnets that are always magnetic, so the ones that you attach to your fridge or you played with as kids. Those are materials that have a permanent magnetism to them. And then you can also create temporary magnets, and temporary magnets are ones where the material, if it's near a magnet, will become magnetic itself, but if you take it away from the magnet, it won't be. So examples of permanent magnets: neodymium, those are those really strong magnets that are hard to pull apart. Alnico, which is a combination of aluminum, nickel, and copper. And cobalt, pardon me, cobalt. And there's other types of combinations of materials that are permanent magnets. The thing that you will find with all permanent magnets is they contain either iron, nickel, or cobalt. Those are your three magnetic elements. Temporary magnets are objects that also have iron, nickel, or cobalt, but they're not permanently magnetized. They only become magnetized if you place them in a magnetic field. So an example of that would be like a compass needle. Compass needles in and of themselves aren't magnetic, but if you place them in the Earth's magnetic field, they will align themselves with the Earth's magnetic field, and it becomes a temporary magnet. So inside a permanent magnet, there are areas within that magnet where the atoms all kind of act together. We call them magnetic domains. And those are just small groups of magnets that act like little magnets themselves. And in a permanent magnet, all the magnetic domains get lined up the same way. They're all aligned with their norths pointing one way and their souths pointing another way. So all your magnetic domains are all permanently aligned in a certain direction. That's a permanent magnet. So what that ends up creating is if all your domains are pointed in such a way that if we call the arrows the norths, all your norths are going to be pointed one direction and the ends of the arrows will be the south. So that creates an overall at this end of the magnet, that creates an overall north. And down at this end, it creates an overall south. So your magnet overall will have a north end and a south end. And these stay lined up this way inside the magnet, even if it's not in a magnetic field. In a temporary magnet, those are materials that still have magnetic domains, but the domains are all aligned in different directions on the inside. And it's not until you put it into some pre-existing magnetic field, like the Earth's magnetic field or some other magnet is brought nearby it, and that causes these domains to all try to align themselves kind of in that magnetic field, the same way a compass needle aligns itself in the Earth's field. And that creates, just temporarily, a slightly north side and a slightly south side. It won't stay like this, though. If you remove that magnetic field out of there, then you go back to being this, randomly organized domains. So an example of this is a paper clip. If you take a paper clip, itself is not magnetic. It won't stick to the fridge or any of those sorts of things. If you bring it near a magnet or even rub it on a magnet, you can actually just temporarily magnetize it. It doesn't stay for long, though. It ends up going back to where it's not magnetized anymore. So magnets have fields around them the same way electric charges have fields around them. And so the magnetic field looks very similar to the electric field. Here's the magnetic field for a bar magnet with a north and a south end, and you can see it's going from the north to the south, stretching in that direction. Here's for the magnetic field for the Earth. Outside the Earth, you can see it's kind of nice and goes from the north to the south. Inside the Earth, it's a little messier because we have layers inside the Earth, the mantle, that's moving around a lot, and there's a lot of motion inside there, and that makes the magnetic field be a little bit crazy on the inside of the Earth, coming out of that iron core. But outside the Earth, it's actually quite nice and rather organized. How do magnets relate to charges? Because that's what we're going to really be getting at. When you move an electric charge around and create a current, it creates its own magnetic field, and that's what an electromagnet is. It's the use of a current, like inside this big electromagnet up here. You turn on the current, it makes this magnetic, and you can use it to pick things up. What's nice about it is you can also turn off the current, at which point it's no longer magnetic. So I can pick up this material, transport it somewhere else, and then drop it. So that's the nice thing about an electromagnet, is the ability to turn on and off, versus a permanent magnet, you don't have that ability. It's always magnetic. So in this situation, you wouldn't want to use a permanent magnet because you could pick the stuff up, but then you could never drop it. So that would be kind of useless. So electromagnets are nice. It comes from the fact that currents create their own magnetic field. The other relationship is something we'll talk about a little bit later on, and that's how if you have a magnetic field and you move it around, you can create a current. So if you have two magnetic fields moving relative to each other, you can create a current. And that's what a generator does. So if you have a generator, this is a hand crank generator, or a picture of a hand crank generator, where you're physically using your hand motion to move this magnetic field, this current in this magnetic field in another one, and then that creates a current which you can use to you know, in this case, run a light bulb or whatever. So that's the purpose of a generator, and that's what they do. So we'll talk more about generators later. For right now, we're going to focus a little bit on this top one, how these currents create their own magnetic fields. So this is your first right-hand rule. You're going to use your right hand, and you're going to use this right-hand rule to determine the direction of a magnetic field around a current. So you take the wire and you put your thumb in the direction that the wire is, and the direction that the current is flowing in the wire, and then you wrap your fingers around. So you're going to physically think about doing this. You won't have the actual wire in your hand, but you'll put your thumb in the direction the current is, and you'll wrap your fingers around. And as your fingers wrap around, that gives the direction of the magnetic field. So if you think about this, the magnetic field is counterclockwise around that current. And we use this right-hand rule to determine the magnetic field. So any wire, if you do it in this direction with the current going that way, if you put your fingers down in that direction, you'll see that the magnetic field is going to go in. It's going to be wrapping around in this direction. Because if you put your thumb in the direction of the current and you wrap your fingers around, it goes in that direction, okay, around the wire. And it's going to be in concentric circles like drawn right here. It'll be stronger towards the wire and it'll get weaker farther away. But the magnetic field is going to be in concentric circles around the wire itself. Okay. Now, when we draw these, it's kind of hard to draw this. It's easier to draw it if it's all flat with the plane of the paper. But sometimes the magnetic field is not pointing; it's in a direction that's not flat with the paper. So we're going to have to come up with a way that we draw things. So anything that's coming out of the paper towards you, we're going to draw that as a dot. And any field line that's going into the paper, we're going to draw it as a circle with an X in it, like that. So that's how we're going to draw these. So for example, if I had a current that was running this way, so assuming that's a nice straight wire, you'll do a better job than I do, I can put my thumb in the direction of that current. So that would be my thumb pointing to the right, excuse me. And as I curl my fingers around, my fingers at the top of the wire, above the wire, come out at me above the wire. So if you think about that, you put your thumb to the right and your fingers curl out towards you, and then they curl in towards you, in towards the paper, away from you, pardon me, at the bottom of the wire. So that's how you would draw this magnetic field. So the magnetic field would be coming out at the top and going in at the bottom, making circles all the way around. And that's how we draw this. So all along this wire you could draw these little dots that indicate the fields coming out at the top and going in at the bottom. Just like that. Okay? So that's how you would draw the magnetic field. If I had a wire going this way with a current in that direction, I would put my thumb pointing up to the, up and to the left, and I would curl my fingers and they would go in on this side and they would come out on this side. So you need to practice this and play around with it. Another way you could do this is suppose the current itself was coming out of the paper. So the current's coming straight towards you. So you're going to point your thumb straight at you and curl your fingers, and you're going to note that your fingers curl this way. They curl around in this direction. So that's what the magnetic field would look like, is circles around the outside, and that's assuming that the current itself was pointing out of the paper at you. Alright, so that's our first right-hand rule, kind of the easiest of all the right-hand rules. So drawing the magnetic field, I'm going to give you a second to draw the magnetic field lines around all four of these pieces of, all four of these different wires. So pause the video for a second, then draw the magnetic fields, and then when you unpause it, you will hear what my answer is. Okay, so for this one that's going up, your magnetic field is going to be going in on this side and coming out on that side. So hopefully that's what you had drawn. For this one with the current going down, pardon me, this one was the current going up. This one, the current going down, the fingers go in on this side and out on that side. And then for the current coming out of the page, we just drew this one on the other sheet. And then for the current going into the page, it's going to be in the opposite direction. Okay, so that would be your magnetic field lines for those various currents. Alright, how we can calculate this magnetic field. First of all, the symbol we use for magnetic field is the letter B. It is a vector, so it would have a vector symbol over the top of it. But again, remember, I can't do that with a PowerPoint, so I usually just do bold print. The unit is called a Tesla. That's an amp per meter. And the way that you find the magnetic field around a wire is you use this formula. Mu naught is a constant called the permeability of free space. It's equal to 4 pi times 10 to the minus 7. I is your current, 2 pi is just 2 pi, and R is the distance away from the wire. And that would need to be in meters. And your I would need to be in amps, and that's how you get amp per meter. And that's how you end up with a Tesla when it's all said and done, because your mu naught has the right unit so that you end up with Tesla. Okay, so there's a couple of problems. I'm just going to do kind of quickly. The magnetic field around a DC current of 25 amps, so that's going to be mu naught 25 amps, because it's mu naught, just to remind you, mu naught I over 2 pi R. That's my current, my magnetic field. And over, so that'll be over 2 pi, and then the R is going to be 0.1, because it's 10 centimeters to the right of the wire. And so you figure out what that number is. So mu naught is 4 pi times 10 to the negative 7, and then 25, and then divided by 2 pi, and then times 0.1. And you figure out that's a number, and that answer is going to be in Tesla. The direction of the magnetic field, you'll need to figure that out too. The current is running vertically upward, and you are to the right of the wire. So that means if the current's running upward, if you do the right-hand rule, then the magnetic field on the right-hand side is going to be pointing into the page in that case. So your answer would be however many Tesla this is, pointing into the page is fine. Okay? Alright, this one allows you to, this problem is going to allow you, ask you to calculate the magnetic field between two wires. The first wire has 5 amps and the second wire is 7 amps. And they want to know what the magnetic field is, the net magnetic field halfway between. So it's at a distance of 5 centimeters from each. So if you do the right-hand rule for this one and point your finger out, your thumb out of the page, your fingers at this point point upward. So the magnetic field due to 1 is going to point upward.